Modeling with exponential and logarithmic functions. Numerous scientific processes found in nature can be modeled with exponential and logarithmic functions. In this lesson, we will deal with population and radioactive decay. The first population function we will look at has to do with the time it takes for a population to double. So the size of a population n at time t can be found by n of t equals n naught times 2 to the power of t over a. That's kind of hard to read. That's a t over a exponent, where n naught is the initial population, t is the time, and a is the doubling time, which is measured in the same units as t. So if you're talking about days, then the doubling time has to be in terms of days. So we've got a certain culture of bacteria, which initially has 10 bacteria, and it's observed to double every 1.5 hours. So we want to kind of make note of what we've been given. The 10 bacteria is the initial, so that would be n naught. And then the doubling time is 1.5 hours, so that's what A is, 1.5. Part A just wants a model for any t hours. We don't know how long, we just want a basic formula. So n of t equals, fill a 10 in for n naught, times 2 to the power of t over 1.5. So that's the basic formula. Part B, estimate the number of bacteria after 35 hours. Now we have a value to fill in for t. So the number of bacteria at 35 hours would be 10 times 2 to the power of 35 divided by 1.5. And when you put that in the calculator, you get 105689838 bacteria after 35 hours, starting with 10. That's how many you end up with. Part C, after how many hours will the bacteria count reach 10,000? So now we've got a final amount. We know the final amount's 10,000. We want to know how long it takes to get there. So 10,000 is 10 times 2 to the power of t over 1.5, and we have to solve for t. So the first thing we'll do is divide by 10, and that gives us 1,000 equals 2 to the power of t over 1.5. Now, I don't want to have a variable exponent. I need to get that down. So the way you get exponents down is you log both sides, and that will move the exponent out in front. So now we have log of 1,000 equals t over 1.5 log of 2. Divide both sides by log 2. And don't put anything in your calculator until you have t by itself. And then finally we would need to multiply both sides by 1.5. So what we're putting in the calculator is 1.5 times the log of 1,000 divided by the log of 2. And that comes out to be 14.95 hours. This one's about squirrels. A gray squirrel population was introduced in a certain county of Great Britain 30 years ago. Biologists observed that the population doubles every 6 years, and now the population is 100,000. So let's write down all the information that we have. It's 30 years have passed. It doubles every 6 years, so A is 6. And we have a final population, n of t is 100,000. What we don't have is n naught, the starting population. So when we fill in our formula, this is our formula again, we would have 100,000 is n naught times 2 to the power of 30 over 6. Divide both sides by 2 to the power of 30 over 6, which is really 2 to the 5th. And in the calculator, that ends up being 3125 squirrels. Part B says estimate the squirrel population 10 years from now. So 10 more years have passed after the original 30. So our total time is 40 years. We started out with 30 years and we've added 10 more to it. So our time is 40. So the number of squirrels we would have after 40 years would be 3125 times 2 to the power of 40 over 6, which is 317480 squirrels. You would want to round down since we can't count partial squirrels. And then they want us to do a graph. So if you're going to do a graph, you just need to leave t as t, and of course in the calculator you actually have to use x. So the formula we're putting into our y equals would be the initial population, 3125, times 2 to the power of t over 6, or actually x in the calculator, over 6. And I've given you a window if you want to try the graph. And then just sketch what you see on your screen, which would look something like this. And then that's good enough for that. Now, if the growth rate involves something other than doubling, a different formula has to be used. So this is an exponential growth or relative growth rate formula. The population at time t is n of t equals n naught times e to the power of rt. N naught is the initial population. R is the growth rate. It will be given to you as a percent. You'll have to change it to a decimal. And T is time. So it says the fox population in a certain region has a relative growth rate of 8% per year. So I know R, 8%, would be 0.08. It's estimated that the population in 2013 was 18,000, and we're starting at 2013. So N naught is 18,000. Part A says find the function that models the population t years after 2013. So we leave the t as a t, 18,000 e to the power of 0.08 t. So that's the general formula for these foxes. Part B, use the function from Part A to estimate the fox population in the year 2021. So 2021 is 8 years later after 2013. So we're finding n of 8, 18,000, e to the power of 0.08 times 8. And that comes out to be 34136. Part C, after how many years will the fox population reach 25,000? So remember, this is our original formula. To the 0.08 t. And we want to know what t is if we end up with 25,000. Divide both sides by 18,000, you can cross out the zeros and you're just left with 25 over 18. Now we need to get rid of e, and remember natural log gets rid of e. So we've got the natural log of 25 over 18 equals 0.08 t, and divide both sides by 0.08. And you end up with 4.11 years. Part D is to sketch a graph. So into the y equals, you'll put 18,000 e to the power of 0.08x. There's the window if you want to try graphing it, and you just do a little sketch of what you see on your calculator, and it'll look something like that. The graph shows the deer population in a Pennsylvania county between 2010 and 2014. Assume that the population grows exponentially. Part A, what was the deer population in 2010? Well, we know that we are using the formula that we just went over, n of t equals n naught e to the RT. And we get the information, what was the population in 2010? That would be year 0, because the x-axis is the years since 2010. And so 0 would be right on 2010, and if you look straight up to the red line, we're at 20,000. And that will be our initial population. That will be n naught, 20,000. Part B, find a function that models the deer population t years after 20,000. Well, we don't have a rate, and we're going to have to figure out a rate. But we know after 4 years, the population was 31,000, because that's a point that they've marked on the graph. So I can fill in the formula with that information. I've got 31,000 is the initial 20,000, e to the power of, we don't know the rate, but we know at 31,000, 4 years had passed. Now we can solve for r. If we divide both sides by 20,000, we can mark out the zeros and have the fraction 31 over 20 is e to the 4r. Natural log both sides. 31 over 20, or natural log of 31 over 20 equals 4r, and divide by 4. And we get that r is 0.1096. So now we've got to plug all that back in to get our formula. So n of t equals 20,000. Sorry, I've run out of room here. E to the power of, and r is 0.1096. T. So that's our basic formula. What is the projected deer population in 2018? Well, 2018 is 8 years after the start year of 2010. So t would be 8. So n of 8 would be 20,000. E to the power of 0.1096 times 8, which is 48,063 deer. Part D, estimate how long it takes the population to reach 100,000. So here's our basic formula again, 0.1096t. And we want to end up with 100,000 deer. So 100,000 equals 20,000 e to the power of 0.1096t. Divide both sides by 20,000 and you have 5. Natural log both sides. Natural log of 5 is 0.1096t, and divide. The time is 14.68 years. The population of Bubblyville was 3,500 in 1980 with a growth rate of 2.7% per year. By what year will the population have doubled? Okay, let's remember our formula. T is n naught e to the RT. So if it doubles, it's twice of what it started with. And so the way you can set up a problem like that, you don't really even need to know what the original population was. We know that we ended up with twice what we started with, 2 times n naught. So we don't have to have that n naught. We have it in this problem, it's 3,500, but we don't really need it. E to the power of, we have r, change it to a decimal, move the decimal 2 places left, 0.027 t. And you can just divide out the n naughts, and they're just going to go away. That's why it doesn't matter if you fill the number in or not. 2 equals e to the power of 0.027t. Natural log both sides. Divide by 0.027. And you get 25.67 years. Now that didn't actually answer the question. They want a year, by what year? And so if you started in 1980 and you add 25.67, you end up with the year 2005. Part B, by what year will the population have tripled? It's going to be the same setup, except instead of starting off with 2 times the initial, you'll have 3 times the initial, and then you'll just go from there, same process. Radioactive decay. The remaining mass, m, of a radioactive material after time t is m of t equals m naught e to the power of negative RT, and then R has its own formula, the natural log of 2 divided by h. H is the half-life, and that will be given to you in the problem. So our first example says the half-life of strontium-90 is 28 years. How long will it take 80% of the sample to decay? Now you have to be careful, this is a little tricky. If the half-life's 28, that's H, and then it says 80% has decayed, and M of T is what you end up with, not how much has gone away. So if 80% has decayed, 20% of the original, of the initial, remains. That's how much you end up with. And when you do 20% of the initial, that would be 0.20 m naught equals m naught e to the power of negative natural log of 2 divided by h, which is 28, and then there's a t. Now I can divide out the m naughts and have 0.20 equals e to the power of negative natural log of 2 over 28 t, and we will natural log both sides. Natural log of 0.20 is negative natural log of 2 over 28 t. Now I can multiply both sides by 28. And then I've got 28 natural log 0.20 equals negative natural log of 2t. Divide both sides by negative natural log of 2. All into the calculator, and you get 3561.13 years. Sorry. That's the answer to the next one. It comes out to be 65.01 years. Now you know what the next answer is going to be. Okay, here's another. Oh wait, that's not the right. A wooden artifact from an ancient tomb contains 65% of the carbon data that is present in living trees. How long ago was the artifact made? The half-life of carbon-14 is 5,730 years. So the 65% is how much is left, and that's what M of T is, how much you end up with. So it's 65%, 0.65 of the original, M naught, equals m naught e to the negative, and then r is the natural log of 2 over h. For this problem is 5730 times t. So divide out the m naughts. And so it's going to be the same process that we had in the last problem. Natural log both sides. natural log of 0.65 is negative natural log of 2 over 5730 all times t. Now you can actually get rid of that fraction all in one shot if you just flip it over and multiply. So what that's going to look like on the other side, the 5730 would now be on top with the natural log of 0.65 over negative natural log of 2. And then that is 3561.13 years. And we're going to finish off with a problem that involves Newton's law of cooling. And it's a big formula, the temperature of a certain object after amount of time t. And in the formula, T of S is the temperature of the object's surroundings. You can see it appears twice in the formula. T naught is the initial temperature of the object. K is a constant that's unique to each type of object. So every object has its own value of K that has been found by previous experiments. Newton's law of cooling is actually used to find time of death when people find bodies and they have to figure all that out. And so we're going to do soup, which is much less gruesome. Now your textbook, instead of writing in the parentheses T naught minus TS, they just use D naught for that. But to me that adds an extra step. So I just fill in the formula with the T naught minus TS from the very beginning. All right, a hot bowl of soup of 210 degrees Fahrenheit is placed in a room that's 65 degrees Fahrenheit. For this type of soup, K equals 0.05. Part A is we want to find a function, and so I've written down everything we know from the beginning. The initial temperature is 210. The temperature of the surrounding area is 65. K is 0.05, and then I filled in the formula right here. And the 65 appears twice because T of S appears twice in the formula. And then the only simplification you can really do inside the parentheses, 210 minus 65 is 145. So our formula T of T is 65 plus 145 e to the power of negative 0.05 t. So now whatever time we have, we can plug it in and see what temperature the soup is, which is going to be part B, sort of. After how long will the temperature of the soup be 100 degrees? So we want to know how long it's going to take it to cool down to 100 degrees. We are ending up with 100. 65 plus 145 e to the negative 0.05 t, and we need to solve for t. So you would subtract 65 from both sides, and that would give you 35 equals 145 e negative 0.05 t. Then divide both sides by 145, and you can reduce the fraction if you want to. It's not really necessary. Just leave it a fraction. You don't want it a rounded decimal that's going to make your answer inaccurate. Now we can do natural log on both sides. 35 over 145 equals negative 0.05 t. And then finally divide by negative 0.05. And it comes out to be 28.42, and our time was in minutes for this problem.